All right. Good. Well, I guess good afternoon. No, it's good evening. Good evening, everybody. Or I guess good afternoon if you watch in the afternoon, or good morning if you watch it in the morning, which I think most of you guys probably will. All right. Well, this is Mr. Arocena, and I'm going to continue talking about static electricity tonight. Yeah. So let's see. The last lesson we talked about Coulomb's law. And let me just write it down here. So Coulomb's law related electrostatic force by way of this equation, KQ1 Q2 over R squared. So this was the electrostatic force between two objects, where K was Coulomb's constant, Q1 and Q2 were the charges, and R squared was the separation distance between them. Now today we're going to talk about the electric field. And the electric field is, how can I put it? I always think of it as some kind of like mystical field that is responsible for the electrostatic force. I guess the best way you can put it. Um, it's, I guess it's a thing that happens when you have two charges together. They just exert this force on each other by way of the electric field. So I guess the best way we can put it is this is what causes electrostatic force. Okay. That's the best description of the electric field. All right, now to calculate the strength of the electric field. The strength of the electric field is based on the strength of the two charges in question. So, because the electric field will affect charges differently, depending on the charge, you can actually measure the strength of the electric field as the amount of force it exerts on some amount of charge. So here, this is the electric field, electric field, electric field. Okay, this is the electrostatic or electric field force, I guess. Electric field force on the charge. Oops, not sure what happened there. And this is the charge. All right, so the electric force that the field exerts, or the strength of the electric field, is basically a measure of how strong the force affects a charge in its immediate vicinity, I guess. In its immediate vicinity. So you can sort of think of it like, okay, if I have a charge here, and I have another charge here, this charge, so we'll call this charge 1, has an electric field that exerts all around it. And then the strength of that electric field is based on how it affects another charge nearby and how much movement or how much force it exerts on this other charge. Okay, so that's what the electric field is. The electric field is just a measure of how strong the charge affects other charges. Oh, hey Connor, shouldn't you be going to bed? It's kind of late. All right, that's strength of electric field. Now, the direction of the electric field is incredibly arbitrary. It's actually good to think that you are here, Connor, because you're not going to be in class tomorrow, just like me. All right, so the direction of the electric field is based on a positive test charge. Again, this is incredibly arbitrary. There's no... I guess I've never looked into why we decide to define the direction of an electric field this way. That's just what we do. So the electric field direction, let's say we have a positive charge. The electric field of this positive charge will be based on how a positive charge moves in relation to this charge. So let's say if I put a positive charge beside another positive charge, I know that this positive charge is going to move away. If I put a positive charge here, it's going to move away. This is just the laws of static electricity at work. So a positive charge has an electric field that effectively radiates outwards. Okay, so positive charges have electric fields that radiate outwards. Now, the only reason that we say they radiate outwards is, again, because for whatever reason, we have decided to arbitrarily choose to define the direction as how a positive charge moves in that field. So so to guess, I could actually erase a bunch of these because the positive charges don't need to be there because I'm hopefully that's the idea. So there we go. So this is the electric field of a positive charge. It just radiates outwards like this. Okay, now a negative charge, the opposite is true for a negative charge because for a negative charge will drag positive charges towards it. So that's kind of the direction of the electric field for a negative charge. So a negative charge has an electric field that drags things towards it. Okay. So there we go. Oops. Didn't mean to erase that arrow, but there we go. So there you go. So that's the direction of an electric field for a positive and a negative charge. Now, interestingly enough, these lines, I'm going to call these are electric field lines. So electric field lines. Okay, this is not the not electric force lines, electric field lines. And that's something that I have to be very careful with, is the electric field is not the same as the electric force. It's just they're very closely related, but not quite the same. Alright, so there you go. So the electric field lines for a positive charge radiate outwards. Electric field lines for a negative charge radiate inwards. And that's all because of our arbitrary decision to say direction is based on positive test charge movement. Okay. All right, now this gives us some interesting things because if it leads to sort of why the electrostatic laws of electrostatics, why they exist in the way they do. Because let's say I put two negative charges beside each other. Let's do positive charges. Positive charges make much more sense. Okay, so the positive charges, they have electric field lines that radiate outwards, like this. So here we go. So here's a positive charge with radiating outwards like this. Okay. So when this happens, one of the things that the electric field lines will do is when they meet each other like this, so here we go. So here they're starting to meet each other like that, meeting each other, eventually meet each other. The one thing they cannot do is they cannot cross each other. So electric field lines, oops, I don't actually need to type field because that symbol is electric field. So electric field lines cannot cross each other. Okay, this is one of the rules when drawing electric field lines. So I'll just say that, yeah, cannot cross each other. So when these field lines hit, since they can't cross into each other, they just kind of like skirt around each other like this. They just get pushed around. So they have to find a way to avoid each other without crossing into each other. So they effectively create this barrier between them. Let's put that in a different color. They create this barrier here between the two charges that they cannot cross. And that would be, I guess, the best way to explain why these two positive charges do not, they don't get close to each other and try to repel each other, because as you get more and more field lines radiating from here, so basically as you get stronger and stronger, charges, you'll have more and more electric field lines leaving the charge, and this barrier gets bigger and bigger. And it's basically like two things trying to push each other, and they can't because of this one rule that the electric field lines cannot cross each other. So that's kind of how you can explain that one rule of electrostatics where things that are the same repel each other. Okay? With positive charges, it's very easy to see that. With negative charges, it's a little more difficult. So I'll go back to here. With negative charges, it's a little more difficult because the field lines travel towards themselves like this. But they exhibit very similar behaviors because they can't cross each other. Those field lines have to come from somewhere. But the end result is still the same. It looks a little awkward though because they're not really pushing each other, but they still have this barrier here between them where they don't cross. Okay, so it's kind of like this invisible barrier where this field line wants to go this way, but not really because there's another field line wanting to go that way also. So they just kind of curve around backwards like this. There we go. So with negative charges, it looks a little awkward or a little different. With positive charges, it's way easier to see with positive charges. And again, that's because of this. Electric field lines do not cross. Do not cross each other. Okay. Obviously, this is kind of limiting because there's only 2 dimensions. In 3 dimensions, you'd have ones going out of the page. So in 3D, the lines can go into and out. In 3D, the lines can go out and in, can go out of page and into page. Okay. But I'm kind of limited in what I can draw here. Anyways, well, there you go. Okay. Now, if I have 2 charges which are of opposite charge sitting beside each other, so like here, we'll actually end up. Oh, wait, this is actually way more different. Anyways, I'll focus on these 2. So if I have 2 charges which are the same, they effectively form one line like this. So all the electric field lines will just run parallel to each other like this. There we go. Like that. So this is kind of what explains why oppositely charged objects attract each other, because the electric field lines, they don't cross, and they can reinforce the same direction they're going in, so they may as well. Okay. Now over on this side, you'd get the same result where these field lines would end up meeting each other like this, and then they would repel each other like that. Now these ones would continue moving this way, something like that. These ones would continue moving this way, and so on. Okay. So that's how you would draw the electric field lines for, I guess, multiple charges. Like that. Now each charge does generate a relatively infinite number of electric field lines, but one thing you can sort of show is that more field lines generally means a stronger field. Just as for a visual representation. So if you want to show a very, very strong electric field, you can just draw lots and lots of electric field lines. Okay, but again, you still have to maintain that one rule where the electric field lines cannot cross each other. So be mindful of that. All right. There's an example of using our equation from earlier. So let's suppose we have a downward force of 6.4 times 10 to the negative 3 newtons acting on a 3.2 microcoulomb charge. What is the direction and magnitude of the electric field? So this is basically a charged particle sitting inside an electric field, which is either generated by another charged particle or generated by some mechanical device. So our equation is as follows. Electric field equals force over charge. We want to know what the electric field strength is, so we'll put in the information we know, 6.4 times 10 to the negative 3 newtons. We have a 3.2 microcoulomb charge. Remember, micro means 10 to the negative 6 coulombs. So this ends up being, I think, let's see, 6.4 divided by 3.2 is 2. And then 10 to the negative 3 divided by 10 to the negative 6 is 10 to the 3. And the electric field have units of newtons per coulomb. There we go. All right. And the direction, now remember the direction of the electric field is the direction that a positive charge is moving in. So if the positive charge is moving in a downward direction, then the electric field will go in the same direction as that positive charge. So in this case, the electric field is going down. The force is going down because that's what it tells us, okay, which means that this charge is moving down, but the electric field is also pointed down because, again, electric field direction is based on how a positive charge moves. If this were a negative charge and it was feeling a downward force of 6.4 times 10 to the negative 3 newtons, the electric field would actually be going up this way because the negative charge moves in the opposite direction of the negative charge moves in the opposite direction of a positive charge, so the electric field goes in the opposite direction that this force is acting in. Okay. All right. Okay, example. Now, electric field and voltage kind of go hand in hand with each other because we define the voltage as, well, if you define voltage this way as a change in electric potential energy, this is what we call voltage, or you'll hear this interchanged with potential difference a lot as well. So potential difference and voltage are the same. Think of this as the amount of work needed to move the charge, and the equation kind of lends itself to that. So voltage is defined as follows. Basically force times distance. So this is a work, or change in energy. This is charge, and this is voltage. Voltage. All right. So voltage is effectively just how much energy it takes to move a charge some distance, I guess. Okay. So this force, I guess we can note this force, this would be the electric force or electrostatic force. Okay. And then this distance here would be distance the charge moves. Okay. Which in reality is just work, so that's why you can group this basically as the amount of work needed on a certain amount of charge, or the amount of work done on a charge. Okay. Now this type of equation is quite common in problems like this, where you want to separate a charge, and you want to know how much voltage I need to apply in order to separate those charges. The most common example right now at this stage of our studies is basically this is what's called a parallel plate capacitor. You've got two parallel plates and you've got a charge and you want to separate them. And now the question is asking us, okay, so we have our two charged plates, we have a distance here of 2.4 millimeters, so that's times 10 to the negative 3 meters. We want to create an electric field it's going this way, the electric field is going this way. We want to create an electric field with a strength of 2 times 10 to the 4 newtons per coulomb. I want to know what the voltage is necessary to do this. Well, the voltage necessary is going to be force times distance divided by Q. So the electric force times the distance I want to move the charge, and divided by the charge itself. Now, the electric field, we can actually show that the electric field the electric field is really just a force per charge. And if I look at these two equations closely, I should see that the electric field, is really already present in my voltage equation. There. So the voltage for this type of situation can easily be described as simply how strong my electric field is times how far apart the plates are. Because what I'm really saying is the voltage is going to be how much energy does a positive charge gain, or how much work do I need to do to move a positive charge from one end of the plate, or from the positive plate all the way to the negative plate. That's basically what it's saying. So this voltage is the amount of work needed to move this charge across this distance. And then we can set those two equations up, and you can see that the electric field fits nicely into here. The electric field fits nicely into here to give us this equation. So this then just becomes, okay, let's do our multiplication. So 2 times 10 to the 4 times 2.4 times 10 to the negative 3. So this gives us altogether 4.8 times 10 to the first, or effectively 48 volts. Yeah, so for this case, I need to supply at least 48 volts in order to separate these two, or this positive charge, to have moved this positive charge from one plate to another. Same can be said if I want to move a negative charge going this way. I can do that also. Or another way to think about it, you can also say, okay, if I take a positive charge, this is how much energy I need to exert to move it so it's sitting right here. And then if I let it go, it goes back this way, and the charge can release some amount of energy. Okay. And this is what we call a parallel plate capacitor. I guess you can call it a very primitive battery. Because anytime we separate charge, we either do work on the charge and store it. So in the case if I'm moving this positive charge this way, I'm doing work on this positive charge to store the energy here. And then if I let that charge go, it'll naturally move across this way, releasing the energy that I've stored on it from keeping it there. Yeah, that kind of acts like a simple battery. All right. Hey, another example. So here, an electron of mass, they're really tiny, has an elementary charge. We stick it in an electric field with the following definition. Notice my units are slightly different in this case, and that's the unit electric field can be expressed in this way because, again, from the previous example, we showed that voltage is electric field times distance. And this can be rearranged to show electric field is voltage divided by distance. So that's why you can express the units of electric field this way as well. All right. So here we're asked to find what is the acceleration of this electron if it is placed in this electric field. Well, in order to find acceleration, we generally need to know how much force is acting, and then we can use Newton's second law like this. So what acceleration is the electron experience? So we need to know how much force this electron feels. And we're going to use, I think I want to use this equation. Okay. I want to use that equation. Okay. The other equation we had for electric field, I'll write it down here. Actually, I don't want to use that. I want to use this one in combination with this. So I want to use these two equations. Okay. I guess in a roundabout way, I did use this one, so I could rearrange it to write this. And then I have another equation for electric field, which is this. And since both of these calculate for electric field, I can set them equal to each other. So I can set the one electric field equation equal to the electric field equation that we had originally, and we can solve for the force. So the force will be based on the voltage, the separation distance, and the charge. Okay, let's see. Do I need to know anything else? I already know what my electric field is. What am I talking about? I don't actually need to set this up this this way. Eraser, because I know what my electric field is. It's given to me, and the problem is this. All right, so let's just set that up. 1.0 times 10 to the 3 equals some amount of force divided by the mass of the electron. So, oh, my math teachers are going to hate me for this, but that's okay. All right, let's calculate that. Do I even need to use a calculator? No, I don't need to use a calculator. See, 9. So I take this, multiply it here, 9.1 times 10 to the negative 31. This would be 9.1 times 10 to the negative 28. Yes, newtons. There we go. Alright, so that's how much force my electron feels. Now I need to figure out how much acceleration. So I'm going to take this force, throw it into this equation. I have the mass of the, that's charge. I have, oh wait, I messed that up. I put the mass instead of the charge in there. Okay, let's redo this equation. It's like that force seems really tiny. I'm supposed to put charge in here, not mass. Getting ahead of myself. So this becomes 1.6 times 10 to the negative 16. Yeah. 1.6 times 10 to the negative 19 times that. There we go. That's better. That's better. That's better. Yeah, getting a little bit ahead of myself. I put the mass in place of the charge. My mistake. My mistake. All right. Well, now that we've got the right force, now I can throw it in that equation. I'm just gonna grab this, and where is my... Oh, I thought I had Sketchbook open. Let's open it up. Nope, wrong one. Did I not open it up? Ugh. There we go. All right. Much better. All right. So, putting that into here. Now my equation, we have force equals mass times acceleration. I have a force of 1.6 times 10 to the negative 16 newtons. Now I can put the mass in, 9.1 times 10 to the negative 31, and I'm solving for acceleration. So we'll divide both sides by this. So my acceleration will be ridiculously high. Let me just do the 1.6 divided by 9.1. So that'll be 0.176, I guess, times 10 to the negative 15, I want to say. No, not negative 15, positive 15. Yes, positive 15. Proper scientific notation, this should be 1.8 times 10 to the 14. This will be in meters per second squared. There we go. There's my acceleration. So this electron will accelerate ridiculously fast in that electric field. Okay. This equation kind of forms the basis of modern day particle accelerators. The only difference is we're not accelerating electrons. Usually accelerate other things. So they don't accelerate as fast because most particles end up being like 2,000 times heavier than an electron. But still very fast. Still very fast. Because it'll hit the speed of light in less than a second at this acceleration. Alright, on to another example. Actually, never mind. I don't have an example. It's your assignment. Alright, there you go. So, your assignment will then be as follows. If you guys have any questions, I should be in the school in the afternoon, so you guys can probably come and ask me then. But yeah, there you go. So there's electric field. And we'll discuss this in more detail on Tuesday, I guess. So electric field defined as force per charge. Voltage defined as... We had different definitions for voltage. Do it force distance over charge, which is also work over charge, which is also change in energy over charge. Oh, I should make mention that E is electric field, and E without the arrow, you have to be very careful about how you define this. So this is electric field vector, and this will mess you guys up a lot, simply because of how we've defined energy. Electric field, no direction. Or energy. So be very, very careful of how you label your electric fields and energy in this unit, because it can be quite confusing, especially when we start talking about how much energy charged particles gain in an electric field, because you'll have several versions of E floating around your equations. So just be mindful of that. Oh, and to get to your question, Connor, weekend was fine, although I really suck at death matches in Overwatch. That's okay. I just play tanks. Alright, we'll see you guys next time.